So let's go ahead and build this dive problem instance. Let's go ahead and build this dive problem instance in Gurobi through the interactive shell. So we're assuming here that you've already installed Gurobi on your machine. So to invoke the Gurobi interactive shell, if you're in Windows, by default your Gurobi installation will have a shortcut to the interactive shell on the desktop. Alternatively, you can open up a command window and simply type in Gurobi. And if you're running on a Linux or OS X platform, you can simply enter gurobi.sh from a terminal in order to open up the interactive shell. So the interactive shell is really just a Python shell with Gurobi libraries imported. So all the code we're about to enter here is really Python code, but if you haven't seen Python before, you should still be able to follow what's going on. So first step to creating any model in Gurobi is to instantiate a model object and to give that model object a name. So we're going to instantiate a model object and we're going to call that model object M. And now when I build my model, I'm going to use the reference to that model M to add all the decision variables and structural constraints that I need to add to the model. So let's go ahead and add our decision variables first. So we have decision variables x1 through x5. In order to add a decision variable to my model, I have to call the addVar method that's associated with my model object. So the name of my model object is M. I'm going to call the addVar method, and I'm just going to go ahead and specify all the parameters associated with decision variable x1. So the parameters I can specify, if you recall, are the lower bound, upper bound, the objective function coefficient, the variable type, and the name. So all the variables in this problem are non-negative. So they're all going to have a lower bound of 0, and they don't have an upper bound. Or an upper bound is, in a sense, infinity. And Gurobi provides a special constant called grb.infinity that you can use if your variable doesn't have a natural upper bound to it. The obj parameter is the objective function coefficient for this decision variable. Recall that our objective function was the total cost of our diet, and x1 represented the number of ounces of food type 1 that we include in our diet. So x1's objective function coefficient is simply the per ounce cost of food type 1, which, if you recall from our data, was 20. The v-type parameter allows you to specify whether a variable is continuous or integer. In our case, we're solving a linear program, so all our decision variables are allowed to be any real number, any non-negative real number, rather. So all our decision variables are continuous, and Gurobi provides a constant called grb.continuous. That will be your v-type if you're solving a linear program with all continuous variables. Just for reference, there are other v-types that you will commonly run into. If you want to constrain your decision variables to be integer, then you would use a v-type of grb.integer. And if more specifically you want to constrain a decision variable to be binary, as if you want to have a decision variable that can only take on 0 and 1 values, then that would correspond to a v-type of grb.binary. But for now, all our decision variables are going to be continuous, so the v-type is simply going to be grb.continuous. And finally, we're going to give our decision variable a name, and that name, let's go ahead and call it food.1, since it represents the number of ounces of food 1 that I consume. Note that it kind of looks like we've given this decision variable 2 names. So the name x1 is going to be the name of this variable in the context of this Python session. Food.1 is going to be the name of the variable if we choose to ultimately write the model out to a file. So a good naming convention that we recommend for decision variables and constraints is to first give a word or phrase that describes what that variable or constraint represents, and then put a period, and then list any subscripts that variable has. Right, so in this case, the subscripts on our decision variables were 1 through 5, which referenced food types. x1 corresponds to food 1, so it had a subscript of 1. So note that you can give your variable a different name in Python than you give to Gurobi. Python naming conventions require that, well, they're standard naming conventions. They don't allow you to include periods in the variable name. So when I define my variable x1, I'm not allowed to define a variable x.1 because that wouldn't be a proper Python, that wouldn't follow the Python naming convention. So let's go ahead and instantiate the rest of our decision variables. So when I instantiate the rest of my decision variables, so the parameters that I specify in the addvar method, they have default values, and it turns out that some of the default values are going to be okay for our purposes. So the default value for a lower bound, for example, is in fact 0. The default value for variable upper bounds is infinity, and the default v-type happens to be grb.continuous. So it's not necessary for us to specify lower bounds, upper bounds, and v-type every time, since we can just allow those parameters to take on their default values. So when I instantiate the rest of my decision variables, I'm only going to specify the parameters that don't take on their default values. So that is, I'm going to specify the objective function coefficient, and I'm going to specify the name of the decision variable. So x2 is the number of ounces of food type 2 that I consume. So food 2 has a per ounce cost of $10. So it has an objective function coefficient of 10, and I'm going to go ahead and call variable x2. I'm going to give it a name. Following my name conventions, I'm going to call that variable food.2. Now I'm going to go ahead and add the rest of my decision variables. Food 3 has a per unit cost of $31, and we're going to call that decision variable food.3. Food 4 has a per unit cost of $11, and we're going to call that decision variable food.4. Finally, food 5 has a per unit cost of $12. Since we're building this model interactively, we're really in the Python shell right now. So if you're curious as to what x1 through x5 actually were, you can go ahead and type in x1, hit enter, and it'll tell you that x1 is in fact a Gurobi var object, and it'll also tell you that x1 is awaiting a model update. So recall that every time we add a decision variable to the model, we're really increasing the size of that model. So when we call the addvar method, the variable that we're instantiating every time we call the addvar method is not formally synced with the model until we call the model update method. So after we've instantiated all our decision variables, we're going to call the model update method, and the model update method is going to add all those decision variables to the model all at the same time. And now if I ask what x1 is, it'll tell me x1, its type is still a Gurobi.var, but it's no longer waiting a model update. That variable is now synced with the model, and it has a name of food.1. And if you're curious as to what exactly the type of m is, type in m, hit enter, and it'll tell you that m is a Gurobi.model object. Currently it has 0 constraints because we haven't added any structural constraints to the model yet. And it has 5 decision variables. So now we've instantiated our decision variables, now we're in a position where we can actually write down our constraints. Right, so our constraints, our structural constraints involve our decision variables, so we need to instantiate the decision variables first. And then once we've instantiated our decision variables, we can write down our 2 structural constraints. So recall that we have a structural constraint corresponding to each nutrient requirement. We can add structural constraints to the model via the addConstr method. The first structural constraint we're going to add is the nutrient 1 requirement that says that we need to consume at least 21 units of nutrient 1. That constraint we've already written down. So the first parameter of the addConstr method is the constraint that you're actually trying to add to the model. And we can simply type in that constraint as an inequality. And Gurobi will know what we're talking about here. So the first parameter is the constraint, which is 2x1 plus 3x3 plus x4 plus 2x5 has to be greater than or equal to 21. And then the second parameter is the name of that constraint, and we'll call that constraint, since it's a nutrient requirement, specifically it's nutrient 1 requirement, we'll call it, following our naming convention, we'll call that constraint nutrient.1. Again, note that the name that we've specified on the left-hand side of the equal sign of all these assignments is the name that we're going to give our decision variables and constraints in the context of this Python session. The name that we give as a parameter to the addVar or addConster method, that's the name that Gurobi is going to use for these variables and constraints. Gurobi has less stringent rules for naming variables and constraints. Specifically, Gurobi allows for periods, so we're going to go ahead. That's why we're going ahead and giving more descriptive names with periods to Gurobi, whereas our Python names are going to have to follow Python naming conventions. So we've added our first nutrient requirement. Our second nutrient requirement says that we have to consume at least 12 units of nutrient 2, and we've written that constraint down as x2 plus 2x3 plus 2x4 plus x5 has to be greater than or equal to 12, and we're going to go ahead and call that constraint nutrient.2. And for the curious, we're able to simply type in those constraints as inequalities, and Gurobi knows what we're talking about because Gurobi has overloaded various operators for us. Gurobi has overloaded the plus, multiplication, and greater than or equal to operators. And you can see this for yourself. If I take 2 times my decision variable x1, the multiplication operator is overloaded, so that when I take a constant times a decision variable, Gurobi knows how to interpret that expression. And similarly, the plus sign is also overloaded, so if I take a linear combination of my decision variables, Gurobi knows how to interpret that linear combination. So the plus and multiplication operators are overloaded so that when we take a linear combination of constraints, Gurobi knows how to interpret that linear combination, and it stores that linear combination of decision variables in an object of type lin expression. The greater than or equal to operator is also overloaded so that when I take a linear expression and say that linear expression is greater than or equal to 21, the greater than or equal to operator is overloaded so that it returns what's called a Gurobi temporary constraint object. It's a temporary constraint because simply typing down constraints without calling the addConster method doesn't do anything. So in order to formally add a structural constraint to the model, I have to pass that constraint into the model by calling the addConster method and specifying that constraint as the first parameter. So now that I've specified all 5 decision variables and all 2 of my structural constraints, I have 2 options. If I query those con1 and con2 Python references that I just created, those are both Gurobi.conster objects, but I'm told that those conster objects are awaiting model update. Right, so constraints, similar to decision variables, expand the size of the model. So it's helpful to be able to add all the constraints to the model at once. So when I call the addConster method, that doesn't formally register the constraint with the model object until I have 2 options. I can either call the model update method like I did before, or I've added all the constraints I want to add to my model. I can go ahead and call the optimize method to solve my problem. And the optimize method will automatically call update for you and will sync any pending constraints or variables to your model. So let's go ahead and just call optimize and solve this problem because we're ready to solve it. So we're solving a problem with 2 rows and 5 columns. So the 2 rows corresponds to our 2 structural constraints, and the 5 column corresponds to the 5 decision variables that we instantiated. And we're told that the problem was solved in 2 iterations, and we got an objective value, so our optimal cost is 1.31 times 10 squared, or $131. So we have the optimal cost of our diet, but we're probably more concerned with what the actual diet consisted of, right? We're more concerned with what food types and how and what quantity did our diet look like. So to get the optimal value for our decision variables, we query an attribute called x. So each decision variable is a var object, and var objects all have attributes. I'll have an attribute called x, which represents the optimal value of that decision variable after we've optimized. So I could take each of my decision variables x1 through x5 in turn and query the x attribute, and that will tell me what food types and in what quantity were in my diet. So let's go ahead and interpret the solution. So when I queried the x attribute of x1, I got back 0, which tells me that I should include 0 ounces of food type 1 in my diet. Similarly, I should include 0 ounces of food types 2 and 3 in my diet. I should include 1 ounce of food type 4, and I should include 10 ounces of food type 5. We can go ahead and just do a quick back of the envelope calculation to make sure that the solution actually satisfies our structural constraints. So we only included foods 4 and 5 in our diet. Let's look at our nutrient 1 requirement. So nutrient 1, we're required to include at least 21 units of. Food type 4 had 1 unit of nutrient 1 per ounce, and food type 5 had 2 units per ounce. So food types 4 and 5, their contribution to nutrient 1 was x4 plus 2x5. And if we evaluate that expression using our optimal solution, we find out that we did in fact consume exactly 21 units of nutrient 1. Let's repeat this for nutrient 2. So for nutrient 2, food type 4 had 2 units per ounce, and food type 5 had 1 unit per ounce. So we're going to evaluate 2x4 plus 1x5. And we're going to find out that we did in fact consume exactly 12 units of nutrient 2. So we satisfied all our nutrient requirements, and we satisfied those requirements exactly. So let's talk about more ways that you can query your model and your solution. So the model object has a method called write, which takes in a file name parameter and writes either the model you just built or the solution out to a file. So what the write method actually does depends on the extension of the file name you specify. So if you specify a .lp extension, that's going to output the model in a human-readable form. If you specify a .mps extension, that's going to output a full precision copy of the model. So which should you choose? Well, it depends on what you're trying to do with this copy of the model. If you're trying to look at the model yourself for diagnostic purposes and you want to verify that the code that you just wrote actually produces the model you think it produces, as if you want to be able to read the model yourself to validate that it does what you think it should do, then you should write out to an LP file. But if your intentions are instead to write out the model to a file so that it can be read in later for future use, and you want to guarantee that you don't lose any precision when you write your model out and read it back in, then you should choose the MPS file format. And finally, the .sol extension will output the solution to a file instead of the model. And note that you can append .gz to any of these extensions, and Gurobi will instead write out a gzipped version of the file. So Gurobi knows how to write out and read in gzipped files. So the model object also has various attributes that you can query, the most notable which are the solver status and the objective value. So ideally when you optimize, Gurobi will return you an optimal solution in a reasonable amount of time. However, the possibility exists that either your model is too difficult to solve in the time limit or the iteration limit that you specify, or that your model simply has no feasible solutions. So the status attribute of the model object will let you know which of these cases you're in. And if Gurobi was able to solve your problem to optimality, or if it was able to at least find a feasible solution, then the OBJ attribute will give you the objective value of the best solution that Gurobi could find. So the var and conster objects also contain attributes that you might be interested in. We already looked at the var attribute x, which gives you the optimal value of your decision variable. So for many applications, you may simply care about the optimal values of your decision variables and nothing else, because the optimal values for your decision variables are what are ultimately going to drive your actual decision-making process. But we're going to also talk about today some other attributes pertaining to sensitivity analysis of your solution. So specifically, the variable attribute RC and the conster attribute pi are attributes that tell you how your optimal cost would change if you were to perturb a constant in one of your constraints. So recall that we have two classes of constraints. we have simple bound constraints that operate on a single decision variable, and we have structural constraints that operate on functions of several decision variables. The RC parameter of the var object stands for reduced cost, and the reduced cost of a variable tells you how much and in what direction the optimal cost would change if you were to perturb a variable bound by a small amount. Then in a similar vein, the pi attribute of the conster object is the so-called dual variable, also known as a shadow price or a bid price, and that attribute tells you how much the objective would change if you were to increase the right-hand side of the structural constraint by a small amount. We'll note that dual prices are also used in a technique called delayed column generation, which is a technique for speeding up really large-scale linear programs. So let's go ahead and interpret both the reduced cost and the dual variables in the context of that diaprob instance that we just built. So the sensitivity analysis tells us what would happen if we perturbed our model attributes by a small amount. So we have to know before we can do this analysis, before we can interpret the dual variables and the reduced costs, we have to know exactly how we can perturb our model. So we've talked about var and conster attributes that Gurobi computes for you. Now let's talk about some attributes that you can set as the user. So we're going to talk about 3 var attributes that you can set as the user. Those are the lower bound, upper bound, and objective coefficient. Those are LB, UB, and OBJ. Constraint attribute that you'd be interested in querying is the right-hand side, or RHS. So note that when we built the model, we've actually already specified values for all these attributes. Either we've specified values explicitly or we've accepted default values. But this shows that after you've built a model, and even after you've optimized the model once, these attributes allow you to perturb either variable bounds, objective function coefficients, or the right-hand sides of your constraints. So we're going to go ahead and go back to our diaprob instance, and we're going to try to answer 2 questions. The first is, how much would your optimal cost change if we were required to consume at least 1 unit of food type 1? And the second is, how would your optimal cost change if you were required to consume an extra ounce of nutrient number 1? So let's answer the first question first. So recall that in an optimal solution, we didn't consume any units of food type 1. So now we're going to ask the question, okay, what if we forced at least 1 unit of nutrient 1 into our diet? So what would happen to our objective if we took the lower bound of x1, which was previously 0, and changed it to 1, and then re-optimized? How much would your optimal cost change? And the answer to that question, by definition, is really just the reduced cost of decision variable x1. So decision variable x1 had a reduced cost of 11 1/3. And what that tells us is if we were to adjust the lower bound of x1 from 0 up to 1, our cost should increase, and specifically it should increase by 11 1/3. So we're going to go ahead and re-optimize in a second. But before we even re-optimize, we can predict what our new objective value is going to be by taking the old objective value and adding the reduced cost of decision variable x1. So recall that the old objective value was 131. The reduced cost of x1 was 11 1/3, so we think our cost is going to go up by 11 1/3 by making this adjustment to the model. And that would give us a new cost of our diet of 142 1/3. So to test that theory, we can go ahead and re-optimize. So I've already adjusted the lower bound of x1 to 1. I can go ahead and re-optimize now, and sure enough, the new optimal cost of my diet is in fact 142 1/3. All right, so to summarize, the reduced cost of x1 was 11 1/3. That tells you when you adjust the lower bound of x1 from 0 to 1 that your optimal cost is going to increase by 11 1/3, and sure enough, when we actually did that experiment, our cost increased from 131 up to 142 1/3. So let's go ahead and answer the second question now. So let's go ahead and reset our x1 lower bound to 0. And now the second question is, how would the optimal cost change if we were required to consume an extra ounce of nutrient 1? So recall that con 1 was our first structural constraint, and that first structural constraint was a constraint on the number of ounces of nutrient 1 that we were forced to consume. The RHS parameter of con1 was 21, which corresponded to the number of units of nutrient 1 that we were required to consume. The question we're asking here is, what would happen if I changed the right-hand side of my constraint from 21 to 22? So what would happen if I now require my diet to include 22 units of nutrient 1? So the answer to that question, by definition, is the dual variable associated with constraint 1. And you can query that dual variable by looking at the conster attribute pi. So the dual variable for constraint 1 was 4 1/3. The interpretation there is that if we were required to consume an extra unit of nutrient 1, that the cost of our diet was going to go up by 4 1/3. So I've gone ahead and perturbed the right-hand side of my first constraint from 21 to 22. We'll go ahead and re-optimize in a second, but first let's go ahead and predict what our new optimal cost is going to be. So our original cost was 131, and we think that cost is going to increase by 4 1/3, according to the dual variable associated with constraint 1. So we would predict that our new optimal cost after we require 22 units of nutrient 1 is going to be 135 1/3. So let's go ahead and re-optimize to see if that's the case. And sure enough, our cost does in fact go up to 135 1/3. All right, so to summarize that, dual variables tell us how much your objective is going to change by if you increase the right-hand side of one of your constraints by 1. In the context of the diet problem, increasing the right-hand side of one of your constraints is akin to requiring an extra ounce of a nutrient. For nutrient 1, that extra cost per unit of nutrient 1 was 4 1/3. And sure enough, when we required an extra unit of nutrient 1 in our diet, the optimal cost of our diet did in fact increase by 4 1/3. So finally, let's show how to write the model we just built out to a file and read it back in. So I'm going to choose the LP format because we're going to want to read this model ourselves. So we're going to want to output the model in human readable form. So I'm going to go ahead and write out to a file called diet.lp. Now let's go ahead and look at what that file looks like. So our problem was one of minimizing. Our objective function was what? It was the total cost of our diet, which was 20 times the number of ounces of food 1 we consumed, plus 10 times the number of ounces of food 2 we consumed, and so on. So these objective function coefficients were in fact they're 21, 10, 31, 11, and 12, which were in fact our per ounce costs. And we had two structural constraints. Note that the names in this file are the names that we gave Gurobi, not the names that we used in Python for our Python references. So our first structural constraint was called nutrient.1. And we wrote the model out to a file after we made the perturbation to our right-hand side. As we wrote out to a file after we perturbed the right-hand side of this constraint to 22. So this constraint says that we require at least 22 ounces of nutrient 1. And our second structural constraint requires that we consume at least 12 ounces of nutrient 2. So we have two structural constraints, and they look like what we expected they would look like. There's a bound section here which is empty. So recall that in a definition of a mathematical program, we assume non-negativity constraints by default. So this bound section would ordinarily list variable bounds, but the bound section assumes non-negativity by default, and since all our variables happen to be non-negative in this case, and had no other simple bounds, our bound section is going to be empty. So we've successfully written our model out to a file. Let's talk about how we would read a model back into a file and analyze that model. So Gurobi provides you a global method called read, which takes in a file name as a parameter, and it returns a model object. So it reads in that file and it returns you a model object, which we're going to call M here, corresponding to the model in that file. So once we've read the file into a model object called M, there's two methods associated with model objects that allow you to access specific decision variables and structural constraints. So the getVar_by_name method allows you to access decision variables, and the getConstr_by_name method allows you to access constraints. And these are both new methods that have been added in version 5.0 of Gurobi. So let's go ahead and read in our diet.lp file. So sure enough, when we read in our diet.lp file, it's telling us we read in a model that has 2 rows, or 2 structural constraints, and 5 columns corresponding to the 5 decision variables that we instantiated. So note that now, if I try to ask Python, what is x1? Well, x1 was what I was calling my decision variables in the previous session of Python, which I've quit. So the scope of those decision variables, x1 through x5, or those decision variable references, the scope of those references was limited to the Python session that I was in. Once I exited Python, those references were lost, but I can reconstitute all those references via the getVar_by_name method. So recall that the decision variable x1 had a name. It was foo.1. So if I want to reconstitute my reference to x1, I can do that by calling the getVar_by_name method and passing in the name of the variable that I want to get a reference to, which was foo.1. So it's helpful to follow a naming convention for your decision variables and constraints, because if you ever want to reconstitute your decision references to your decision variables and constraints in a future session, you're going to need to reference the names that you specified in your original session when you built the model to begin with. And you can reconstitute references to your constraints in a similar fashion by using the getConstr_by_name method. And recall that our nutrient constraints had names of nutrient.1 and nutrient.2. And in fact, you can verify that the con1 and con2 references do in fact refer to the structural constraints we think they refer to, because if I query the RHS attribute of con1, it's 22. Recall that I perturbed the right-hand side of constraint 1 from 21 to 22 before I wrote the model out to a file. I can go ahead and reset that right-hand side back to 21, its original value. And I can re-optimize, and sure enough, I get back my optimal cost of 131. So recall that in our original solution to the diet problem, our optimal diet included only 2 food types. So sometimes when we inspect the solution to our original model, we figure out that we actually had constraints that we forgot to include in the model, but that we would actually like our solutions to follow. So it's possible that in this case, maybe we look at our solution and we decide that our diet should include at least 2 ounces of at least 3 different food types, as maybe we want to have a more diverse diet. So in order to do this, I need to create binary decision variables. And those binary decision variables, yj, are going to be defined to equal 1 if we consume at least 2 ounces of food type j, and 0 otherwise. And I'm going to relate those new decision variables y to my original decision variables x via constraints that look like xj is greater than or equal to 2 times yj. So that's going to force xj to be at least 2 if yj equals 1. So that requires us to add binary decision variables to our model. We're going to use the same addvar method to add binary decision variables, but we're going to specify a v-type of grb.binary. So I'm going to add 5 binary decision variables to the model. I'm going to call the update method to sync those decision variables to the model. Now I'm going to add constraints. Let's say that y1, let's see, x1 has to be at least 2 times y1. X2 has to be at least 2 times y2, and so on. And so let's go ahead and re-optimize and see how our solution changes. So we added an additional constraint to our model, so we would expect our cost, the cost of our optimal diet to increase. And in fact, it increased by a pretty significant amount. It increased from an original cost of 131 up to a new cost of 216. Forgot to add a constraint there. So I also need to add a constraint that says that I need to consume at least 3 food types. So I need to add a constraint that says that the sum of my binary variables has to be greater than or equal to 3. All right, now let's re-optimize and see what happens. Yeah, so now we note that in our diet, we do in fact include at least 2 ounces of 3 different food types in our diet. So that's just an example of how including binary variables in your model can increase what you're capable of actually modeling. So in particular, if you have a problem where you have to make discrete yes or no decisions, typically you will need to include binary variables in your model. Binary variables allow you to make sort of all or nothing decisions. All right. So we just solved a problem instance with only 5 decision variables and 2 constraints. Typical linear programs will have thousands, if not millions, of decision variables and constraints. So we need to be able to generalize what we just did to an arbitrary number of nutrients and food types. So let's go ahead and generalize the diet problem. So I'm going to let set I index my set of nutrients, and I'm going to let set j index my set of nutrients. My data is going to be, so Cj is the cost per ounce of food type J. Aij specifies the nutrient densities, and Bi's specify minimum daily requirements for each nutrient. And my decision variables xj are going to be the number of ounces to consume of food type J. Before we write down the generalized diet problem, let's go ahead and introduce some notation that we're going to need. In order to be able to write down realistically sized LPs in a compact form, we're going to need to incorporate some set and summation notation. We're also going to frequently use a symbol that kind of looks like a funny looking E that is read as N. So we need to be able to sum up large sets of decision variables. We're going to use the sigma notation to do so. When I use the sigma notation, under the sigma, I'm going to specify the set that I'm summing over. So in this case, I've defined a simple set I, which is only going to include the integers 1, 2, and 3. If I say take the sum over I and I of AI times xi, what that means is I'm going to let little I take on the values 1, 2, and 3. So I'm going to let little I equal 1, 2, and 3. When I let little I equal 1, I get A1x1. When I let little I equal 2, I get A2x2. And when I let little I equal 3, I get A3x3. And the summation says I'm going to sum up all 3 of those terms. I'm going to use similar notation for constraints. If I wanted to write down a large set of constraints all at once, I can write down what that constraint looks like in terms of my index I. And then after that constraint, I write for all I and I. And the for all I and I is going to say, all right, I've written down a single constraint, but I'm really going to instantiate this constraint for every I, little I, in the index set, capital I. So in this case, xi less than or equal to bi is going to translate into a separate constraint for I equaling 1, 2, and 3. So this allows us to write down large sets of constraints that all have the same general form. It allows us to write down large sets of constraints all in one shot. So let's apply this notation to generalize the diet problem. So my objective function generalized is the total cost of my diet. So I get the cost of my diet by looking at each food type in turn. I write down the cost for each food type, and then I sum that cost over all 5 food types. So my cost for a specific food type j is going to be Cj xj, and the total cost of my diet is going to be Cj xj summed across all 5 food types, or all food types j and j. My structural constraints, I'm going to have a structural constraint for each nutrient type I and I. Now let's think about what that nutrient constraint would look like for a specific nutrient I. So for a specific nutrient I need to figure out how many ounces or how many units of nutrient I consume. I get that by taking each food type J's nutrient I density, which is Aij, multiplying that by the xj, which is the number of ounces of that food type that I consume. So Aij xj gives me food type J's contribution to nutrient I. Summing that contribution over all 5 food type or all food types j is going to give me the total number of units of nutrient I that I actually consume. And that total has to be greater than or equal to bi, which is the minimum requirement for food type for nutrient I. Now I thought all about that in terms of a specific nutrient I, but that logic applies no matter which nutrient I'm talking about. So I can write down this constraint for all I, little I, in the nutrient set denoted by capital I. And finally, I add non-negativity constraints, which look like xj greater than or equal to 0 for all food types j. The generalized model that we wrote down translates pretty naturally into Python code. So in this little code snippet, we're assuming that all the data has been instantiated. So we're assuming that C, A, and B have all the data loaded into them already, and that our index sets j and I are already populated. So first I'm going to add a decision variable for each food type j and j. I'm going to do that using Python list comprehension syntax. So I call the addvar method for each little j in the index set capital J, and the square bracket notation around that addvar call is Python list comprehension syntax, which is going to return us a list of variables that we're going to use later on when we instantiate our structural constraints. So this one line of code instantiates all my decision variables. I call a model update to sync all those decision variables with the model. And finally, I add down my structural constraints. I'm going to call the add constr method to add structural constraints. Each of my structural constraints has a summation in it, but Python provides a method called quicksum that allows us to easily sum up large sets of decision variables. So in this case, we're going to be quicksumming our nutrient density Aij times the corresponding decision variable xj, and we're going to be summing this expression over all food types j in the food type set denoted by capital J. Quicksum returns a linear expression, which is the linear combination of these decision variables. And we're going to set that linear expression to be greater than or equal to our nutrient requirement bi. And we're going to do that. We're going to repeat this process of adding a constraint for every nutrient I in the constraint set capital I.